Hello there, and welcome to Sleep Orion. Maybe you've had a long day at work, trudging through obligations and responsibilities that seem to pile higher with each passing hour. Maybe your mind is still racing with thoughts you cannot seem to quiet, lists of things undone, worries about tomorrow. Or perhaps you simply find peace falling asleep while thinking about the mysteries of the deep ocean, about expeditions into the unknown, about the quiet dedication of scientists and sailors who ventured far from home in search of knowledge. Whatever brings you here tonight, this journey is for you. You don't need to do anything now but rest. Let your thoughts slow down like a ship easing into calm waters. Allow your breathing to soften, each breath flowing in and out like gentle waves against a hull. Notice your body feeling lighter, as if the currents themselves are carrying you away from the concerns of land, away from the weight of daily life, into a space of quiet wonder and gradual sleep. Tonight we drift into one of history's greatest scientific voyages, the Challenger expedition of 1872 to 1876. A journey that transformed a warship into a vessel of discovery, that sent scientists and sailors across every ocean on Earth, that dredged the mysterious floor of the deep sea to reveal secrets hidden since the formation of the planet itself. This was the voyage that gave birth to oceanography as a true scientific discipline. Before Challenger set sail, the ocean depths were almost entirely unknown, a realm of speculation, myth, and fear. Sailors had crossed the surface of the seas for thousands of years, following trade winds and ocean currents, navigating by stars and sun. But what lay beneath, in those lightless depths where pressure built to crushing intensity, remained as mysterious as the surface of another planet. After Challenger returned, humanity possessed real knowledge. There were thousands of preserved specimens in museums and laboratories. There were detailed maps showing underwater mountains and valleys. There were temperature profiles revealing how cold water from the poles flowed along the ocean floor toward the equator. There were chemical analyses showing the composition of seawater from surface to seafloor. There was proof that life existed even at the greatest depths, adapted to darkness and pressure in remarkable ways. The ship traveled 68,890 nautical miles, the equivalent of circumnavigating the globe nearly 3 times at the equator. But the voyage was not a race around the world. It was a methodical, systematic survey. The expedition stopped at 362 stations scattered across all the world's major ocean basins. At each station, the ship would heave to, essentially stopping in place. Weighted lines would be lowered to measure depth, sometimes paying out miles of rope before touching bottom. Dredges and trawls would be deployed to sample the seafloor and the water column, hauled up hours later filled with mud, rocks, and living creatures. Thermometers would be sent down to record temperatures at various depths. Water samples would be collected for chemical analysis. Weather observations would be recorded. The ship's position would be determined with precision using celestial navigation. All of this information would be carefully written into logbooks, and specimen jars would be labeled with station numbers, dates, locations, and depths. The journey would take 3 years, 7 months, and 3 days, from December 21, 1872, when Challenger departed Portsmouth, England, until May 24, 1876, when the ship returned to Spithead. During those years, the crew and scientists would experience tropical heat and Antarctic cold, violent storms and flat calms, the monotony of long ocean passages and the excitement of new discoveries. They would visit remote islands where European ships rarely called. They would probe waters no scientific instruments had ever reached. They would collect specimens that would change understanding of marine biology, geology, chemistry, and physics. The expedition would discover approximately 4,700 new species of marine life, nearly doubling the number of known marine organisms. It would definitively prove that complex life could exist at the greatest ocean depths, disproving theories that predicted a lifeless abyss below a certain depth. It would map the contours of the ocean floor, revealing features as dramatic as any mountain range or valley on land. It would discover the deepest point measured anywhere on Earth at that time, a depression in the western Pacific that would later be named the Challenger Deep. It would gather data that would take decades to fully analyze and would fill 50 volumes totaling over 29,500 pages when finally published. But before any of that could happen, before the first dredge went over the side or the first temperature measurement was taken, the idea of the expedition had to be conceived, planned, and brought to reality. And to understand how revolutionary this expedition was, we need to understand the state of ocean knowledge, or rather the lack of knowledge, in the years before Challenger sailed. In the middle decades of the 19th century, the ocean remained one of Earth's last great mysteries. On land, explorers had mapped most of the continents. The interiors of Africa and Australia were still being explored, and the polar regions remained largely unknown, but the basic geography of the landmasses was established. The ocean, covering more than 70% of the planet's surface, was a different matter. Its surface was well traveled. Trade routes crisscrossed the Atlantic and Pacific. Naval vessels patrolled important straits and channels. Whaling ships hunted across vast expanses of open water. But below that surface, knowledge faded rapidly. How deep were the ocean basins? Some estimated a few hundred fathoms. Others suggested thousands. A few speculated that the deepest parts might be bottomless, descending to the very center of the Earth. There was no systematic data, only scattered soundings taken by individual ships, often unreliable due to the difficulties of the measurement. What covered the ocean floor? Some imagine bare rock, scoured clean by powerful currents. Others envisioned soft mud, accumulated over the ages, perhaps hundreds of feet deep. A few suggested that volcanic activity might create underwater mountains, but there was no way to verify such ideas. What was the temperature at depth? Logic suggested it should be cold, colder than the surface. But how cold, and did temperature change gradually or in distinct layers? No one knew. A few isolated measurements had been taken, lowering thermometers on ropes, but the data were scattered and often contradictory. Most intriguingly, could life exist in the deep sea? This was perhaps the most debated question of all. Many prominent scientists believed in something called the azoic zone, a depth beyond which no life could survive. The reasoning seemed sound. At great depths, the pressure would be enormous, far beyond what any known organism could withstand. The darkness would be complete, preventing any plants from growing and thus eliminating the base of the food chain. The temperature would be near freezing, if not below. The water might lack oxygen, having been cut off from the atmosphere for centuries or millennia. Under such conditions, they argued, life could not exist. Below a certain depth, perhaps 500 or 1,000 fathoms, the ocean floor must be utterly lifeless, covered only in the fine sediment that drifted slowly down from above. Others disagreed. Some naturalists pointed to the few specimens that had been brought up from considerable depths, proving that at least some organisms could survive in deep water. They suggested that the deep sea might be full of life, just different from the life familiar from shallow coastal waters. A few even speculated that the deep ocean might serve as a refuge for ancient forms, organisms that had evolved in the distant past and then survived unchanged in the stable environment of the abyss, protected from the changes that had swept the surface world. This idea of living fossils in the deep sea gained traction in the 1860s and 70s, particularly after the publication of Charles Darwin's On the Origin of Species in 1859. Darwin's theory proposed that species changed over time through natural selection, adapting to their environments. If that were true, then surely the deep sea, with its extreme conditions, would produce unique adaptations. And if the deep sea environment had remained stable for millions of years, perhaps species there had evolved slowly or not at all, preserving ancient forms. Thomas Huxley, one of Darwin's strongest supporters, argued that the deep sea might contain what he called zoological antiquities, creatures that represented the predominant life forms of past geological ages. He suggested that in the tranquil depths, protected from the upheavals that affected shallow water and land, ancient species might persist virtually unchanged. Louis Agassiz, a prominent naturalist despite his opposition to Darwin's theory, independently suggested that the deep sea might contain representatives of earlier geological periods. The idea captured scientific imagination. The deep ocean might be a kind of time machine, preserving living examples of extinct lineages. But these were just ideas, speculation based on limited evidence. The truth was that almost nothing was known for certain about the deep ocean. And lack of knowledge breeds both fear and fascination. Stories of sea monsters, giant squid, and other terrors of the deep persisted in maritime culture. These tales had ancient roots, going back to classical mythology with its Scylla and Charybdis, its Kraken and Leviathan. Sailors swore they had seen impossible things. Were such reports pure fiction, or might there be real creatures in the depths that occasionally ventured to the surface? The ocean was thus a realm of questions without answers, of theories without data, of imagination untethered to observation. It was a scientific vacuum waiting to be filled. And into that vacuum would come HMS Challenger. The practical impetus for deep ocean exploration came from an unlikely source, the telegraph industry. In the 1850s and 60s, companies began laying submarine cables across the ocean floor to enable rapid communication between continents. The first successful transatlantic cable was laid in 1858, though it failed after only a few months. Improved cables followed, and by the 1860s, reliable telegraphic communication between Europe and North America was established. More cables were planned for other ocean crossings. These cables, expensive and technically challenging to manufacture and lay, needed to rest on the seafloor, often at depths of thousands of fathoms. Engineers and businessmen suddenly had urgent practical reasons to care about the nature of the deep ocean. What was the seafloor made of? Would sharp rocks cut the cable? Would strong currents sweep it away or bury it in sand? Would marine organisms attack the protective covering? How could the cable be reliably anchored? How could breaks be located and repaired? To answer these questions, cable companies funded surveys of proposed cable routes. These surveys included soundings to determine depth and samples of bottom sediment to determine composition. The data gathered were fragmentary, focused on specific routes rather than comprehensive understanding. But they demonstrated that systematic deep ocean exploration was technically feasible and could yield valuable information. The scientific community took notice. If ships could be equipped to sound and sample the ocean floor for commercial purposes, surely similar equipment could be used for scientific research. The question became how to organize and fund such research on a scale large enough to produce meaningful results. In Great Britain, several scientists began advocating for a major oceanographic expedition. William Benjamin Carpenter, a physiologist and naturalist, was among the most vocal. Carpenter had broad scientific interests and had become fascinated by the ocean during research on marine invertebrates. He believed that understanding the ocean was crucial for understanding Earth as a whole, and he worked tirelessly to convince others of this view. Carpenter wrote papers and gave lectures arguing for systematic ocean research. He emphasized both the scientific value, the fundamental knowledge to be gained, and the practical applications, improved navigation, better weather prediction, support for fisheries and cable laying. He lobbied government officials and cultivated relationships with military leaders. He understood that mounting an expedition of the necessary scale would require government support, specifically the cooperation of the Royal Navy. Another key figure was Charles Wyville Thomson, a professor of natural history at the University of Edinburgh. Thompson had participated in 2 preliminary oceanographic cruises aboard HMS Lightning in 1868 and HMS Porcupine in 1869 and 1870. These brief expeditions, each lasting only a few weeks and exploring waters around Britain and the North Atlantic, had proven that deep-sea exploration was feasible and scientifically productive. During the Lightning and Porcupine cruises, Thompson and his colleagues had collected specimens from depths exceeding 2,000 fathoms. Many of these were previously unknown species, demonstrating the rich diversity of deep-sea life. They had also taken temperature measurements showing that the deep ocean was stratified, with colder water at depth, and that different water masses with distinct characteristics could be identified and traced. These findings, while preliminary, suggested that a much larger expedition could produce revolutionary results. Thompson became convinced that a circumnavigation focused on deep-sea research would transform oceanography from a collection of isolated observations into a comprehensive science. He worked with Carpenter to develop a proposal for such an expedition, outlining the scientific objectives, the equipment and personnel needed, and the expected results. Together, they approached the Royal Society of London, Britain's premier scientific institution, seeking official support. The Royal Society, founded in 1660, had a long history of promoting scientific research and advising the government on scientific matters. The Society took the proposal seriously. A committee was formed to evaluate it, and after deliberation, the Royal Society formally recommended to the British government that a circumnavigation for the purpose of deep-sea research be undertaken. The timing was favourable. Britain in the 1870s was at the height of its imperial power. The Royal Navy was the largest and most powerful in the world, with ships and personnel stationed around the globe. The British government could afford to dedicate resources to scientific exploration, seeing it as a demonstration of national prestige and a source of practical knowledge that might enhance British commercial and military power. In 1871, the government agreed to support the expedition. The Royal Navy would provide a ship and crew at full Navy pay. The Royal Society would select the scientific staff and oversee the scientific program. It was an unusual arrangement, a collaboration between a civilian scientific institution and a military organization. But it would prove remarkably effective, combining naval discipline, seamanship, and resources with scientific expertise and objectives. The ship selected for the expedition was HMS Challenger, a wooden corvette of 2,306 tons displacement. She had been launched in 1858 at the Woolwich dockyard on the River Thames. Over the subsequent years, she had served in various capacities, including a period on the North America and West Indies station. By 1871, she was due for a refit, making her available for conversion to a research vessel. HMS Challenger was not a particularly large ship by naval standards of the time, measuring 226 feet in length. She was not especially fast, capable of perhaps 12 knots under steam and similar speeds under sail in favorable winds. But she had qualities that made her suitable for the expedition. She was strongly built, important for surviving storms and rough seas during a voyage that would last years. She had ample space below decks that could be converted to laboratories and storage. She was equipped with both sail and steam power, providing flexibility in different conditions. Under sail, she could make progress without consuming coal, important during long ocean crossings. Under steam, she could maintain position while conducting observations or maneuver precisely when needed. The Admiralty estimated that converting Challenger from warship to research vessel would require approximately 6 months of planning and work. The ship was taken to the Royal Navy's dockyard at Sheerness on the River Medway in June 1872. The transformation that followed was extensive and carefully planned. 15 of Challenger's original 17 guns were removed. Warships of that era carried batteries of cannon for combat. These were heavy, took up considerable space, and were unnecessary for a scientific voyage. Removing them created space that could be used for other purposes and reduced the ship's weight, making her more stable and improving her handling characteristics. The ship's spars, the masts and yards that carried the sails, were reduced in size and number. This made the ship easier to handle with a smaller crew and reduced the height of the masts, again improving stability. A fully rigged sailing ship with tall masts could be top-heavy and difficult to manage in strong winds. For an expedition that would need to stop frequently and maintain precise positions while conducting observations, ease of handling was more important than maximum speed. Laboratories were fitted out on the upper deck and below. The main laboratory, located on the upper deck, was equipped with tables for sorting and examining specimens, shelves and cabinets for storage, good lighting through large windows and skylights, and ventilation to remove fumes from preserving chemicals. A separate chemistry laboratory was set up for analyzing water samples, equipped with balances, glassware, reagents, and a furnace for heating materials. Additional workspace was created below decks for processing specimens and storing collections. A special dredging platform was built extending from the ship's side. Dredging and trawling would be central to the expedition's work, and the equipment needed to be deployed and recovered efficiently. The platform allowed the heavy dredges to be swung out over the side of the ship, lowered into the water, and then brought back aboard without interfering with the normal operation of the vessel. Winches were installed for raising and lowering the equipment, powered by steam when needed but also operable by hand. Storage was a major concern. The expedition would last for years and visit remote locations where supplies would be unavailable. The ship needed to carry everything that might be needed for the scientific work. Thousands of specimen jars were loaded aboard, ranging from small vials for tiny organisms to large jars for bigger specimens. These were filled with alcohol, the primary preserving fluid. Alcohol was also needed for fuel in burners and for various chemical procedures, so large quantities were stored in barrels and tanks. Chemicals for analysis and preservation filled numerous crates. Labels, paper, notebooks, and other materials for recording data were packed in waterproof containers. Drawing supplies for the expedition's artist, photographic equipment and chemicals, dissecting tools, microscopes, and countless other items were carefully stowed. The ship needed to be essentially a floating laboratory, complete and self-sufficient for years at a time. The dredging and sounding equipment deserved special attention. Several types of dredges were built or acquired. The main dredge consisted of a heavy iron frame about 4 feet wide, with a net of strong rope attached. The frame would be dragged across the seafloor, scraping up sediment and any organisms in its path. The weight of the frame, several hundred pounds, kept it pressed firmly against the bottom. A variation on the main dredge included mop heads attached to the leading edge of the frame. These were literally the mop heads used to swab the ship's deck, bundles of rope fibers. When dragged across the bottom, the fibers would sweep organisms from rocks and stir up creatures buried in sediment, improving the collection. It was a simple but effective innovation. Smaller dredges and trawls were designed for specific purposes. A beam trawl, with a wide opening held open by a wooden beam, could be towed through the water at mid-depth to catch swimming organisms. The size of the mesh could be varied depending on the target, fine mesh for small creatures and larger mesh for fish. Different designs were used for different bottom types, heavy dredges for rock and coral, lighter ones for soft mud. For measuring depth, sounding was a fundamental operation. The traditional method involved lowering a weighted line until it touched bottom. The line was marked at regular intervals, typically 25 fathoms, 150 feet, with flags or tags indicating depth. Sailors would pay out the line carefully, watching the marks pass over the side. When the line went slack, indicating the weight had reached bottom, the depth could be read from the last mark to go over. This sounds simple but was challenging in practice, especially in deep water. Challenger carried 181 miles of Italian hemp rope specially manufactured for sounding. This rope needed to be strong enough to support its own weight when hanging vertically in the water, plus the weight of the sounding lead, but thin enough that vast quantities could be carried. Each sounding in deep water required miles of rope to be carefully paid out and then, much more laboriously, hauled back in. The sounding weight itself was often ingeniously designed. A simple weight would just tell you when you hit bottom. But a hollow weight with a valve at the bottom could capture a sample of the seafloor. As the weight settled onto the bottom, sediment would be forced up into the hollow interior through the valve. When lifted, the valve would close, trapping the sample. This allowed geologists to examine seafloor composition without deploying a separate dredge. Temperature measurement in the deep ocean required specialized instruments because ordinary thermometers could not withstand the pressure and would give incorrect readings. The primary thermometer used on the Challenger expedition was the millicasella thermometer, named after its inventors. This clever device used a curved mercury tube with two small indicators inside. As the thermometer was lowered through water of varying temperatures, the mercury would expand or contract. The indicators would be pushed along by the mercury, one marking the maximum temperature encountered and the other marking the minimum. After the thermometer was brought back up, it could be read to determine both the warmest and coldest temperatures it had experienced during its descent and ascent. By deploying multiple millicasella thermometers at different depths, the scientists could build up a profile of how temperature varied with depth. The method was not perfect. It assumed that the warmest water was always at the surface and the coldest at depth, which was generally but not always true. And it provided no information about temperature at specific depths, only the extremes. Later in the expedition, a more sophisticated instrument would be tested, the reversing thermometer. This device could record the temperature at a specific depth. It consisted of a thermometer in a protective case that could be inverted, or reversed, by a spring mechanism triggered by a weight sliding down the suspension cable. When the thermometer was reversed, the mercury column would break at a constriction, locking in the temperature at that moment. Multiple reversing thermometers could be sent down attached to the same cable, each triggered at a different depth, providing a detailed temperature profile. Though still being perfected during the Challenger expedition, this type of thermometer would become standard for decades. Water sampling required capturing seawater from specific depths without contamination from other depths. Various types of water sampling bottles were used or invented during the preparation. The basic principle was a container that could be opened and closed at depth. The bottle would be lowered with valves open, allowing water to flow through freely as it descended. At the desired depth, a weight called a messenger would be sent sliding down the cable. When the messenger hit the bottle, it would trigger a mechanism that would snap the valves closed, trapping water from that depth. Multiple bottles could be deployed on the same cable at different depths. The scientific staff selected for the expedition brought diverse expertise and backgrounds. Charles Wyville Thompson, a scientific director, would oversee all research and have final authority over the scientific aspects of the voyage. Thompson was 52 years old when the expedition departed, a distinguished professor with extensive knowledge of marine invertebrates and a vision of what the expedition could accomplish. He was driven, passionate about the work, but also practical, understanding the challenges of conducting research at sea and managing relationships with the naval crew. John Murray would prove to be one of the expedition's most valuable members. Canadian-born, 27 years old at the start of the voyage, Murray had studied medicine and natural history but had not completed a formal degree. He had experience at sea, having worked on a whaling ship. This background gave him practical seamanship skills that the other scientists lacked. Murray had a gift for observation and analysis, seeing patterns in data that others might miss. He would work closely with Thompson and would eventually take over the direction of the scientific report when Thompson died before its completion. John Young Buchanan, the expedition's chemist, was 25 years old and had studied at the University of Glasgow. He would be responsible for all chemical analyses of water and sediments, a daunting task that would continue for years after the expedition's return. Buchanan was meticulous and patient, qualities essential for the painstaking work of chemical analysis with the equipment available in the 1870s. Henry Nottage Moseley, 27 years old, brought expertise in marine invertebrates, particularly corals, sponges, and other sessile organisms. Moseley was a keen observer of nature and would also take an active interest in the lands visited, collecting terrestrial as well as marine specimens and recording ethnographic observations about the peoples encountered. His journal would become the basis for a popular book about the voyage. Rudolf von Willemoes-Summ, a German zoologist, was 24 years old and specialized in microscopic marine organisms. These tiny creatures, invisible to the naked eye, would prove to be extraordinarily abundant and diverse in ocean waters. Willemoes-Summ's expertise would be crucial for understanding the base of the marine food web. His early death during the voyage would be a significant loss. Frank Evers Bed served as prosector, the person responsible for dissecting specimens. Many organisms needed to be dissected to examine their internal anatomy, both for identification and for understanding their biology. This was skilled work requiring both anatomical knowledge and manual dexterity. Bed's work would provide crucial information for the scientists studying the collections after the expedition's return. John James Wild filled a unique role as the expedition's official artist and secretary. In the 1870s, photography was still in its early stages and underwater photography was impossible. Color photography did not yet exist, and even black and white photography was cumbersome, requiring long exposures and delicate handling of glass plates and chemicals. For documenting specimens, particularly their natural colors and three-dimensional forms, there was no substitute for a skilled artist. Wild would create thousands of drawings and paintings during the voyage, providing the primary visual record of many specimens and operations. He would also maintain expedition records and assist with other tasks. The naval complement was led by Captain George Strong Nares, an experienced and respected officer. Nares was 41 years old and had extensive experience in Arctic waters, having participated in an Arctic expedition in 1852–54. He was known for his skill in navigation and his ability to handle ships in difficult conditions. His presence would be reassuring during the challenging portions of the voyage, particularly in Antarctic waters and while navigating through island groups. Commander John McLear served as second-in-command and would remain with the expedition for its entire duration, providing continuity even after Nares departed midway through the voyage. McLear was a capable officer who maintained good relations with both the naval crew and the scientific staff, helping to ensure smooth cooperation between the two groups. Thomas Henry Tizard, though officially part of the naval crew rather than the civilian scientific staff, had experience with hydrographic surveys and oceanographic observations. He would contribute significantly to the physical measurements and would later help write the official account of the expedition. His presence demonstrated that some naval officers had genuine scientific interest and expertise beyond their military duties. The crew numbered about 216 sailors and marines at the start of the voyage, along with 21 officers, for a total complement of 237. This was a substantial company to house, feed, and keep occupied during a voyage of years. Many were experienced seamen, but some were young recruits for whom Challenger would be an introduction to life at sea. The petty officers and boatswains who supervised work would be crucial for maintaining discipline and efficiency. The relationship between the naval crew and the scientific staff required careful management from the start. They came from different backgrounds and cultures. The sailors were accustomed to strict naval hierarchy and discipline. The scientists were civilians used to academic freedom and debate. The sailors saw the ocean as something to be crossed, an obstacle or a highway depending on perspective. The scientists saw the ocean itself as the object of study, with depth and delay justified by the observations they enabled. Establishing mutual respect and understanding would be essential. The scientists needed to appreciate the sailors' skills and the demands of shipboard operations. The sailors needed to understand the importance of the scientific work and the requirements it imposed. The officers would mediate, ensuring that both the ship's safety and the expedition's scientific objectives were served. On December 21, 1872, with preparations complete and supplies loaded, HMS Challenger departed Portsmouth, England. The weather was cold and grey, typical for an English winter day. A crowd gathered to see the ship off, including dignitaries from the Royal Society and the Admiralty. Families of the crew said their farewells, aware that it would be years before they saw their loved ones again. Some would never return, claimed by disease, accident, or the dangers of the sea. Others would desert at foreign ports, unable to bear the monotony or the hardship. But on that December day, spirits were high with anticipation and excitement. They were embarking on something unprecedented. The ship moved slowly down the English Channel, adjusting to the sea after months in port. The sails were set and the rigging tested. The laboratories were checked to ensure everything was properly secured. The first meals were prepared and served, the first watches stood. The routine of shipboard life began to establish itself, rhythms that would govern daily existence for years to come. The first major stop was Lisbon, Portugal, reached in early January 1873. This was a relatively short passage, allowing the crew and scientists to shake down, to identify problems and make adjustments before venturing farther afield. Some equipment was found to need modification. The procedures for deploying and recovering the dredges were refined based on initial experience. The scientists organized their laboratories and began to establish workflows for handling specimens. From Lisbon, Challenger proceeded to Gibraltar, the British fortress guarding the entrance to the Mediterranean. Here additional supplies were loaded, and the ship was readied for the Atlantic crossing. The expedition would not enter the Mediterranean on this voyage, the focus was on the open ocean basins. From Gibraltar, the route led south to Madeira, the Portuguese island group off the coast of Morocco, and then to the Canary Islands. These subtropical islands provided the first taste of warm weather and the first opportunities for truly deep ocean work. The waters around the islands dropped quickly to great depths, allowing soundings and dredges in water over 2,000 fathoms. The scientists began to develop their routines for handling the material brought up by the dredges. Each haul was an event, with officers and crew helping to sort the contents. The material would be spread on sorting tables on deck. The first step was removing the obvious specimens, the large organisms visible to the naked eye. These would be placed in jars of preserving fluid or set aside for immediate examination. The remaining material, seemingly just mud and sand, would be carefully washed through sieves of different mesh sizes. Remarkably, each sieving would reveal more organisms, tiny creatures that had been invisible in the mud. Even after multiple washings and sievings, examination under microscope would reveal even smaller organisms, including single-celled foraminifera and radiolaria, whose beautiful shells would become a major focus of study. The sheer abundance and diversity of life was immediately apparent. Every haul contained dozens of species. Many were familiar from shallow water, or at least clearly related to known groups. But many were entirely new, representing forms that had never been seen before. The scientists realized that they were only scratching the surface, that a thorough study of the collections would take years or decades. In February 1873, Challenger began the crossing of the Atlantic from the Canary Islands toward the West Indies. This would be the first major open ocean transect, with multiple stations across the width of the Atlantic basin. The route went southwest, crossing shipping lanes and then entering less traveled waters in the center of the ocean. At each station, the same procedures were followed. The ship would heave to, essentially stopping by adjusting the sails to balance each other. The position would be determined by celestial observations, measuring the angle of the sun above the horizon at noon and consulting tables to determine latitude. Longitude was more challenging, requiring accurate timekeeping and careful calculations, but the ship's chronometers and the skill of the navigator provided reliable results. A sounding would be taken to determine the depth. This was often the most time-consuming part, especially in deep water. The weighted line would be lowered, the sailors watching the marked rope pay out over the side. 2,000 fathoms required nearly 15,000 feet of rope, almost 3 miles. In calm conditions, it might take 2 hours for the weight to reach bottom. The slightest current would cause the rope to drift, making it difficult to judge when the weight had actually landed. Experience and careful observation were needed to detect the subtle slackening of the line that indicated touchdown. Once the depth was known, decisions would be made about what other operations to conduct. Temperature measurements using multiple millicursella thermometers would usually be taken. Water samples might be collected from several depths. A dredge or trawl might be deployed, though not at every station as the process was so time-consuming. Weather and sea conditions were always recorded, building up data on atmospheric patterns over the open ocean. The Atlantic crossing revealed one of the expedition's most significant findings. The ocean floor was not flat but varied dramatically in depth. There were deep basins where soundings exceeded 2,000 fathoms, descending over 12,000 feet below sea level. There were underwater ridges where the depth decreased to less than 1,000 fathoms. Most notably, there was a north-south ridge running roughly down the center of the Atlantic. This mid-Atlantic ridge had been suspected from earlier cable-laying surveys, but Challenger's systematic soundings confirmed and mapped it in much greater detail. The ridge rose thousands of feet above the surrounding seafloor. In some places it came within a few hundred fathoms of the surface. It extended from far north in the Atlantic down toward the south, apparently running the entire length of the ocean. What could cause such a massive underwater mountain range? The scientists of the 1870s did not know. It would be another 80 years before the theory of plate tectonics would explain that mid-ocean ridges are spreading centers where new ocean floor is created as tectonic plates pull apart. But even without that understanding, the discovery of the ridge was profound. It showed that the ocean floor had structure, that it was not simply a monotonous plain but had geological features as dramatic as any on land. The temperature measurements were equally revealing. At the surface, water temperature varied with latitude and season as expected. In the tropics, surface water was warm, often over 80 degrees Fahrenheit. Farther north or south, it was cooler. This made sense based on the amount of sunlight received and seemed consistent with everyday experience. But below the surface, a different pattern emerged. Temperature decreased with depth, rapidly at first and then more gradually. At a few hundred fathoms down, the temperature might be 60 degrees. At 1,000 fathoms, it might be 40 degrees. At 2,000 fathoms, it approached freezing, often just a few degrees above 32 degrees Fahrenheit. This was true even in the tropics, where surface water was warm. The deep ocean was uniformly cold, regardless of latitude. This finding suggested something remarkable about ocean circulation. If the deep water was cold everywhere, even at the equator, it must be coming from somewhere cold. The only places cold enough were the polar regions. Therefore, water must be sinking at high latitudes and flowing along the bottom toward the equator. This implied a vast overturning circulation, with water sinking at the poles, spreading through the deep ocean, and eventually rising somewhere to return to the surface. This circulation would have enormous implications for climate, transporting heat from the equator toward the poles and cold water in the opposite direction. It would affect the distribution of nutrients, with deep water carrying dissolved minerals that could support life when brought back to the surface. It would influence the distribution of marine organisms, creating highways and barriers for dispersal. Understanding this circulation would become a central goal of oceanography. In April and May 1873, Challenger made a detour from the West Indies north to Bermuda and then Halifax, Nova Scotia, crossing the Gulf Stream twice. This powerful current, flowing north along the coast of North America and then eastward across the Atlantic toward Europe, was well known to sailors who used it to speed passage to Europe and avoided it when sailing south. But what was the Gulf Stream exactly? Was it a surface phenomenon or did it extend to great depths? How wide was it? How sharp were its boundaries? Challenger's measurements provided answers. The Gulf Stream was revealed to be a relatively narrow ribbon of warm water, perhaps 50 to 75 miles wide at its core, flowing through cooler surrounding ocean. The temperature contrast was sharp, several degrees difference over just a few miles. The current extended down several hundred fathoms but did not reach the bottom, where cold water from the polar regions flowed in the opposite direction. This structure, a fast surface current overlying a slower deep current flowing the opposite direction, would be found in other parts of the ocean as well. It demonstrated that the ocean had both horizontal circulation, the currents that sailors navigated, and vertical circulation, the overturning that the temperature measurements suggested. From Halifax, Challenger returned south to Bermuda, then sailed east to the Azores, those isolated volcanic islands in the middle of the Atlantic. From the Azores, it was back to Madeira and then south to the Cape Verde Islands off the coast of West Africa. By August 1873, the expedition had been at sea for 8 months and had conducted dozens of stations. The patterns were becoming clear. The ocean floor had varied topography. The deep water was cold. Life existed at all depths sampled. But there was still so much more to learn, and the expedition had barely begun. From Cape Verde, the ship sailed southeast and then west, reaching St. Paul's Rocks, a tiny cluster of rocky islets barely breaking the surface in the middle of the equatorial Atlantic. These rocks were geologically fascinating, representing pieces of the Earth's mantle thrust up through the ocean crust. They were also treacherous for navigation, small and low-lying, invisible until dangerously close. Challenger stopped to survey the rocks and collect geological samples, adding to the expedition's diverse data. Continuing south, the ship reached Fernando de Noronha, a Brazilian island, and then Bahia, now called Salvador, on the Brazilian coast in September 1873. This was the first extended port stop since leaving the Canary Islands months earlier, and both crew and scientists welcomed the opportunity to go ashore. Fresh food was obtained in abundance, particularly fruits and vegetables that were welcome after weeks of preserved rations. Water barrels were refilled. The ship underwent inspection and minor repairs. The men had a brief respite from the constant motion and confinement of shipboard life. The Brazilian coast provided opportunities for observing coastal and coral reef ecosystems. The scientists collected specimens in shallow water, exploring tide pools and reef flats. They observed the rich diversity of tropical marine life, the brilliantly colored fish and invertebrates, the complex structure of coral reefs. This shallow water work complemented the deep sea focus, providing comparative context. From Brazil, Challenger turned east again, crossing the South Atlantic toward Africa. This passage, from Bahia to the Cape of Good Hope, took several weeks and included multiple stations. One of these, in late September, produced a haul from a depth of over 2,600 fathoms, nearly 16,000 feet, over 3 miles deep. The pressure at such depths exceeded 4 tons per square inch, yet the dredge brought up living creatures, including sea cucumbers, worms, and other organisms clearly alive when collected. This definitively disproved the azoic zone theory. Life was not limited to shallow depths. Even at pressures that would crush most organisms, even in total darkness, even in water just above freezing, complex multicellular life existed. The adaptations that made this possible would become a major focus of biological study. How did deep-sea organisms withstand pressure? How did they find food in the darkness? How did they reproduce and disperse in an environment so different from shallow water? The expedition touched at Tristan da Cunha, perhaps the most remote inhabited island on Earth. This volcanic island, rising steeply from the South Atlantic, supported a small population who survived by farming, fishing, and occasionally provisioning passing ships. The arrival of Challenger was a rare event for these isolated people, providing news from the outside world and a market for their produce. From Tristan da Cunha, the ship continued east and south, reaching Cape Town, South Africa, in late October 1873. This marked the end of the Atlantic phase of the expedition and the beginning of perhaps the most challenging phase, the work in the Southern Ocean around Antarctica. Cape Town would be the last major port before venturing into those frigid, dangerous waters. The ship underwent significant maintenance, with hull and rigging inspected and repaired. Coal bunkers were filled, as steam power might be needed in ice-choked waters where sailing was difficult. Supplies were loaded for what would be months at sea before reaching Australia. The scientists organized their collections, packing specimens carefully and preparing reports to send back to London. These reports provided the Royal Society and the Admiralty with updates on the expedition's progress and preliminary findings. They generated excitement back in England, with newspapers reporting on the discoveries and the public following the voyage with interest. Charles Wyville Thompson wrote to colleagues describing the wealth of material being collected and the challenges of processing it all. He expressed excitement about the deep-sea life but also concern about how long it would take to study everything properly. Already it was clear that the expedition's work would extend far beyond the voyage itself, that the specimens and data being collected would provide research opportunities for decades. In early December 1873, with preparations complete, Challenger departed Cape Town heading southeast into the Southern Ocean. The weather changed quickly as the ship left the shelter of the African coast. The wind increased, swinging around to the west, the direction of the prevailing westerlies that circle Antarctica. The temperature dropped. The sea state built, with waves growing larger and the ship's motion becoming more pronounced. They were entering the roaring 40s, the latitudes between 40 and 50 degrees south known for fierce winds and rough seas. The expedition's goal was to explore the Southern Ocean as thoroughly as time and conditions permitted, to probe south toward the Antarctic ice, to take measurements that would reveal the characteristics of the cold water that flowed north into all ocean basins. But this would be dangerous work. The Southern Ocean had a reputation as the most challenging waters on Earth, and that reputation was well earned. The first stops were at the Prince Edward Islands, small volcanic islands that were among the most remote land in the region. These islands were bleak and windswept, supporting only sparse vegetation, but they teemed with wildlife. Seals hauled out on the beaches in large numbers. Seabirds nested on the cliffs and islands, including several species of albatross and petrels. The scientists collected specimens and made observations before continuing southeast. The Crozet Islands were reached next, another isolated archipelago. The weather was worsening, with frequent gales sweeping across the ocean. The ship pitched and rolled, making work difficult. Securing equipment became a constant concern, as loose items could slide across the deck or be washed overboard. Below decks, the motion made simple tasks challenging and sleep difficult. From the Crozettes, Challenger continued to the Kerguelen Islands, reaching them on January 7, 1874. These islands, larger than the previous stops but equally desolate, were often called Desolation Island, a name that captured their character. Rocky and barren, swept by constant wind and frequent rain or sleet, Kerguelen was nonetheless scientifically fascinating. The expedition spent several days exploring, surveying the complex coastline, and conducting scientific work in the surrounding waters. Then came the push south toward the Antarctic Circle. The ship sailed into increasingly cold conditions, with the temperature dropping well below freezing. Ice began to appear, first as small pieces floating in the water and then as larger masses. Icebergs became frequent sightings, some of enormous size. These floating mountains of ice, carved from Antarctic glacier and ice shelves, drifted north until they melted, sometimes taking years to completely disappear. The icebergs were beautiful and terrifying. In daylight, they could be seen from miles away, towering walls of blue-white ice. But at night or in fog, they were invisible until dangerously close. The ship's speed was reduced, and constant watches were maintained. Several times, Challenger maneuvered to avoid bergs that loomed suddenly from the mist. On February 14, 1874, the expedition crossed the Antarctic Circle at 66 degrees 33 minutes south latitude. This was as far south as they would go. Pack ice, the sea ice that forms on the ocean surface in polar regions, blocked further progress. Attempting to push through would risk becoming trapped as the ice closed around the ship, potentially crushing the hull. Many ships had been lost to ice, their crews forced to abandon ship and try to survive on the ice until rescue, if it came. But reaching the Antarctic Circle was itself an achievement. Challenger was conducting scientific observations closer to the South Pole than any previous oceanographic expedition. The temperature measurement showed water barely above freezing at all depths. The dredges brought up sediments rich in diatom shells, microscopic algae that bloomed in vast numbers during the Antarctic summer when sunlight returned. These diatoms formed the base of the Southern Ocean food web, supporting krill, which in turn fed whales, seals, and seabirds. The expedition documented the enormous populations of whales in Antarctic waters. Multiple species were observed, including blue whales, the largest animals ever to exist on Earth, fin whales, humpbacks, and southern right whales. These great whales migrated to Antarctica each summer to feed on the abundant krill, then returned to warmer waters to breed. Their presence demonstrated the richness of the Southern Ocean ecosystem despite the harsh conditions. Seals were equally abundant, hauled out on ice floes or swimming in the icy water. Several species were observed and collected, including leopard seals, Weddell seals, and crab-eater seals. Seabirds followed the ship constantly, including species adapted specifically to Antarctic conditions. Some, like the emperor penguin, spent their entire lives in the far south. In late February, with winter approaching and ice conditions worsening, Challenger turned north. The expedition had gathered crucial data from Antarctic waters, but pushing their luck further would be foolish. The ship sailed northeast, stopping at Heard Island, another remote and desolate speck of land in the southern Indian Ocean, before continuing toward Australia. The passage from Antarctica to Melbourne took several weeks, with the weather gradually improving and the temperature rising as the latitude decreased. Multiple stations were conducted along the way, building up a picture of how the cold Antarctic water spread northward, gradually mixing with warmer water from lower latitudes but remaining identifiable as a distinct water mass. By late March 1874, Challenger reached Melbourne, Australia. The warmth and greenery of Australia was a stark contrast to the ice and rock of Antarctica. The crew and scientists had spent months in some of the harshest conditions on Earth, and the comfort of Melbourne was deeply welcome. The ship underwent extensive maintenance. The scientific collections were organized and some specimens were sent back to England. Reports were prepared describing the Antarctic work. And everyone enjoyed time ashore, walking on solid ground, eating fresh food, and sleeping in beds that didn't move. Melbourne was a growing colonial city, and the arrival of the Challenger expedition generated considerable public interest. Lectures were given at the university and to public audiences. Specimens were displayed. The scientists met with local naturalists and geologists, exchanging knowledge and specimens. The expedition's work was becoming known beyond scientific circles, capturing popular imagination. The discoveries being made were proof that scientific exploration could reveal wonders. From Melbourne, the expedition continued east along Australia's southern coast to Sydney, arriving in April. Sydney provided another welcoming port and another chance for rest and resupply. The ship was now well past the halfway point of the voyage, having spent 15 months at sea and having explored the Atlantic and Southern Oceans. But more than half the work remained, with the vast Pacific Ocean still to be crossed and explored. When Challenger resumed the voyage in June 1874, the route led northeast from Sydney to Wellington, New Zealand. This leg crossed the Tasman Sea, a body of water known for rough conditions but also for interesting oceanographic features. The sea floor here was complex, with deep basins separated by underwater ridges. Volcanic activity was evident in some areas, with signs of recent geological processes. Wellington, on New Zealand's North Island, provided another pleasant stop. The expedition spent time exploring the islands, which had unique flora and fauna resulting from their isolation. The scientists collected terrestrial as well as marine specimens, adding to the breadth of the expedition's data. New Zealand's Maori people were observed and interactions documented, adding ethnographic information to the expedition's reports. From New Zealand, Challenger headed northeast into the tropical Pacific, stopping at Tonga and Fiji. These island groups represented a dramatic change from the cold waters of Antarctica or the temperate climate of New Zealand. The temperature was high, often over 80 degrees, and the humidity was intense. The water was warm and clear, its deep blue color indicating low productivity compared to the rich waters of higher latitudes. But tropical waters had their own fascinations. Coral reefs surrounded many islands, creating complex habitats teeming with life. The diversity of species on and around reefs was extraordinary, with hundreds of species of fish, corals, mollusks, and other organisms visible in even a small area. The scientists devoted considerable effort to documenting reef communities, recognizing their ecological importance. The structure of coral reefs themselves was a subject of study. How did reefs form? How fast did they grow? What determined their distribution? Charles Darwin had proposed a theory of reef formation, suggesting that fringing reefs could become barrier reefs and then atolls as islands slowly subsided. Challenger's observations provided data testing this theory, generally supporting it. The people of Tonga and Fiji were welcoming, providing assistance and local knowledge. Some came aboard as guides or pilots for navigating through reef-studded waters. The expedition's artists made sketches of the islands and their inhabitants. The expedition was not just studying the ocean but documenting the Pacific world in its breadth. From Fiji, Challenger sailed west and north to Cape York at the tip of Australia, passing through waters of the Great Barrier Reef. This massive reef system, the largest biological structure on Earth, required careful navigation. Coral reefs lurked just beneath the surface, invisible in deep water but deadly to wooden hulls. Charts were incomplete, and constant vigilance was necessary. But the Great Barrier Reef also provided unparalleled opportunities for studying reef ecosystems. The voyage continued north and west from Cape York through the Arafura Sea, with New Guinea to the north and Australia to the south. The ship called at the Aru Islands and Kai Islands, small remote groups in what is now Indonesia but was then the Netherlands East Indies. The heat and humidity were oppressive, making work below decks uncomfortable. But the marine life continued to astound, with every dredge bringing up new species. Amboina, now called Ambon Island, was reached in October 1874. The island had a long history as a center of the spice trade, and its natural history reflected complex biogeographic patterns. From Amboina, the expedition sailed to Ternate, another historically significant island. These waters had been explored decades earlier by Alfred Russel Wallace, the co-discoverer with Darwin of evolution by natural selection. Wallace had documented the sharp division in wildlife between Asian and Australian types, a biogeographic boundary now known as the Wallace Line. Challenger's oceanographic work added context to Wallace's biological observations. From Ternate, the route went north toward the Philippines, passing east of Celebes, now called Sulawesi. The expedition called at Zamboanga on Mindanao and then Iloilo on Panay before reaching Manila on Luzon. The Philippines archipelago, with its complex geography of islands, straits, and deep basins, provided rich opportunities for study. The nearby Mindanao Trench, one of the deepest places on Earth, was a particular target of interest, though the expedition did not reach its deepest point. The voyage continued to Hong Kong, arriving in late November 1874. Hong Kong was a major British port, and the expedition found familiar faces and welcome supplies. The scientists were able to process the enormous accumulation of specimens from recent months. The ship underwent maintenance after prolonged time at sea. But Hong Kong also marked a significant change in leadership. Captain Nares received orders to take command of a British Arctic expedition attempting to reach the North Pole. This was considered a prestigious assignment, and Nares could not refuse. He departed Challenger, taking with him Pelham Aldrich and several other officers and crew members. Frank Toole Thompson assumed command of the ship for the remainder of the voyage. John McLear, the second in command, remained and provided continuity. But the change in captains was significant, and there was a period of adjustment as the new command team settled in and established their working relationship with the scientists. After several weeks in Hong Kong, Challenger departed in early January 1875, heading south through the Philippines. The ship took a different route through the islands than on the inbound journey, allowing new areas to be surveyed. From the Philippines, the expedition headed east into the western Pacific, turning southeast toward New Guinea. The northern coast of New Guinea was still largely unexplored by Europeans. The interior of the island was unknown, inhabited by indigenous peoples still living traditional lifestyles. The expedition collected specimens from coastal waters and made brief excursions ashore, but did not attempt to penetrate inland. From New Guinea, Challenger sailed northeast to the Admiralty Islands and then north into the western Pacific. This leg of the voyage would prove to be one of the most significant of the entire expedition, as the ship crossed over some of the deepest parts of the world ocean. The Pacific Ocean, the largest single feature on Earth's surface, contained within its expanse the planet's deepest trenches and highest underwater mountains. As Challenger sailed north from the Admiralty Islands, the scientists conducted multiple soundings, each one probing deeper than the last. The process of sounding in such deep water was extraordinarily laborious. Miles of rope had to be carefully paid out, watching for the subtle signs that would indicate the weight had touched bottom. The rope itself weighed so much that distinguishing between the weight reaching bottom and the rope simply stretching under its own mass was challenging. Experience and careful attention were required. On March 23, 1875, at station number 225, located in the western Pacific between Guam and Palau, the crew conducted a sounding that would become historic. The weighted line was lowered, marked rope paying out over the side. The sailors watched the marks pass, counting the depth. 1,000 fathoms, 6,000 feet. 2,000 fathoms, 12,000 feet. Still the line kept going. 3,000 fathoms, 18,000 feet, over 3 miles deep. The rope continued to descend into the abyss. 4,000 fathoms, 24,000 feet. Finally, at 4,475 fathoms, the line went slack. The weight had touched bottom. This translated to 26,850 feet, over 8,184 meters, more than 5 miles below the surface. The measurement was so extreme that the scientists decided to verify it with a second sounding. The line was hauled back up, an exhausting process that took many hours. Then it was sent down again, and the second sounding confirmed the first. The ocean floor at this location descended to a depth greater than any previously measured. The pressure at the bottom would be over 8 tons per square inch, a crushing force almost beyond comprehension. This discovery would prove to be one of the expedition's most famous findings. The depression, later recognized as part of the Mariana Trench, would eventually be named the Challenger Deep in honor of the expedition. Modern measurements using sonar and other advanced technology have refined the depth, finding that the deepest point of the Challenger Deep is nearly 11,000 meters, about 36,000 feet, even deeper than the Challenger expedition measured with rope and lead weight. But the discovery that oceanic trenches existed, descending far below anything previously imagined, was revolutionary in 1875. What could exist at such depths? The pressure was unimaginable. The darkness was absolute. The temperature was near freezing. Yet when dredges had been lowered to great depths elsewhere, they had brought up living creatures, proving that life had adapted even to those extreme conditions. The organisms collected from deep water showed remarkable specializations. Many had reduced eyes or no eyes at all, since sight was useless in perpetual darkness. Some had developed bioluminescence, the ability to produce light through chemical reactions, using it to attract prey, communicate with potential mates, or confuse predators. Deep-sea fish often had unusual body forms compared to their shallow-water relatives. Many had large mouths and expandable stomachs, allowing them to consume prey larger than themselves, an important adaptation in an environment where food was scarce and encounters with prey were infrequent. Others had evolved into ambush predators, sitting motionless on the seafloor with lures or other attractants to bring prey within reach, conserving energy in an environment where every calorie mattered. The adaptations extended beyond just morphology to physiology and behavior. Deep-sea organisms had different metabolisms, often slower than shallow water species, reflecting the scarcity of food and the cold temperatures. They had different reproductive strategies, with some species producing small numbers of large eggs and providing parental care, while others broadcast vast numbers of tiny eggs into the water, relying on chance for some to survive and develop. They had different ways of finding mates in the vastness of the deep ocean, using bioluminescent signals or chemical cues to locate each other in the darkness. The discovery of the Challenger Deep and the other scientific work conducted in the Western Pacific represented the culmination of years of methodical observation and data collection. The expedition had traveled from the Atlantic to Antarctica, across the Indian Ocean, through the archipelagos of Southeast Asia, and now into the deepest parts of the Pacific. Each station added pieces to a puzzle, and gradually a comprehensive picture of the world ocean was emerging. The deep sea was not a uniform, featureless void. It was a complex, varied environment with mountains and trenches, with different water masses carrying distinct temperature and chemical signatures, with diverse life adapted to every niche from the surface to the greatest depths. As Challenger prepared to continue north from the deepest sounding toward Japan, the scientists and crew could take satisfaction in what they had accomplished. But the voyage was far from over. Thousands of miles of ocean remained to be crossed, hundreds of additional observations to be made, countless more specimens to be collected and preserved. The work would continue for another year before the ship finally turned toward home, and even then, the analysis and publication of results would occupy decades. But on that day in March 1875, watching the sounding line disappear into water over 5 miles deep, they had touched the deepest abyss on Earth and brought back proof that even there, the ocean held secrets waiting to be revealed. The voyage north from the Challenger Deep toward Japan took Challenger through waters that varied dramatically in character from day to day and mile to mile. The Western Pacific, vast beyond easy comprehension, covered nearly 64 million square miles, making it larger than all the landmasses on Earth combined. Within its expanse lay everything from shallow coral seas to the deepest abysses on the planet, from isolated volcanic islands to sprawling archipelagos, from areas of extreme productivity to biological deserts. Each day brought new observations, new specimens, new data that would eventually contribute to understanding this enormous portion of Earth's surface. The waters between the Mariana Trench and Japan presented oceanographic conditions that differed markedly from areas previously studied. The Kuroshio Current, the Pacific equivalent of the Atlantic's Gulf Stream, carried warm water northward along the western edge of the Pacific Basin. This powerful current, flowing at speeds of up to 4 knots in its core, transported heat from the tropics toward temperate latitudes, moderating the climate of Japan and creating rich fishing grounds where different water masses met. The route to Japan passed through the Mariana Islands, though the ship did not stop at every island in the chain. These volcanic islands, rising steeply from the ocean floor, were scattered across hundreds of miles of open water. Some were inhabited, with small populations living traditional lifestyles modified by contact with European traders and missionaries. Others were uninhabited, too small or too remote to support permanent settlement. Each island had its own unique character, its own complement of species, its own geological history. Time was becoming a concern for the expedition. They had been at sea for over 2 years, had crossed 2 major ocean basins, had explored Antarctic waters and tropical archipelagos. While the scientific work remained fascinating and productive, with every dredge bringing up new discoveries, both crew and scientists felt the pull of home. Letters from family had piled up at port stops, reminders of the lives they had left behind. Some men had children they had never met, born during the voyage. Others had received news of deaths, funerals they could not attend. The plan was to complete the circumnavigation, crossing the North Pacific to the Americas and then returning across the Atlantic to England, but this would still require more than a year of additional travel. The Pacific crossing alone would take months, followed by work along the American coast, passage around South America, and the final Atlantic crossing. They were past the halfway point of the voyage, but much work remained. Efficiency became more important, focusing scientific effort on stations that would provide the most valuable data rather than stopping everywhere possible. The scientists had to be selective, choosing locations that would fill gaps in their understanding or test specific hypotheses rather than simply collecting observations everywhere. This required careful planning and sometimes difficult decisions about what to prioritize. Every station required hours or even days of work, and there were only so many hours available before the need to return home became pressing. The physical toll of the voyage was also becoming apparent. The constant motion of the ship, the irregular sleep schedules dictated by watches and scientific work, the monotonous diet of preserved food supplemented only occasionally with fresh provisions, all wore on the men's health. Some suffered from chronic seasickness that never fully resolved. Others developed various ailments, from skin conditions to digestive problems to respiratory infections. The ship's surgeon did what he could, but medical knowledge and capabilities in the 1870s were limited. Yet morale remained generally good. The sense of shared purpose, the excitement of discovery, the camaraderie that developed during long months together, all helped sustain spirits. The officers worked to maintain order and discipline without being oppressive. Regular routines provided structure. The periodic port stops offered respite and renewal. And the awareness that they were accomplishing something significant, something that would be remembered and valued, gave meaning to the hardships. Japan was reached in April 1875, with Challenger anchoring at Yokohama. Japan had only recently opened to foreign contact after centuries of isolation, and the expedition was among the early European scientific visitors to Japanese waters. The scientists were impressed by Japanese knowledge of natural history and by the sophisticated culture they encountered. Japanese naturalists visited the ship, and specimens were exchanged. The expedition collected in Japanese waters, adding species from this biogeographic region to their growing collection. Yokohama provided a major stop for rest, resupply, and ship maintenance. The vessel had been at sea almost constantly for over 2 years with only brief stops at ports. The hull needed attention, the rigging required repairs, and equipment needed to be replaced or serviced. The scientists used the time to organize their collections, to update their records, and to prepare reports that would be sent back to England via mail packets. Charles Wyville Thomson wrote extensively during the stop in Japan, describing to the Royal Society the wealth of material that had been collected and the patterns that were emerging from the data. He noted that life had been found at every depth sampled, decisively disproving the Azoic zone theory. He described the temperature structure of the ocean, with cold bottom water from polar regions spreading through the deep ocean basins. He reported on the varied topography of the ocean floor, the ridges and trenches that had been discovered. And he expressed both satisfaction at what had been accomplished and awareness of how much work remained, both in completing the voyage and in analyzing the results once the expedition returned home. John Murray also wrote during the Japanese stop, his letters showing his growing understanding of ocean sediments. Murray had become particularly interested in the materials dredged from the seafloor. He recognized different types of sediment and began to understand what they revealed about ocean processes. In shallow water near continents, sediments consisted mainly of material eroded from land, clay, and silt carried by rivers and deposited offshore. In deeper water far from land, sediments were composed primarily of the shells of microscopic organisms that lived in the surface water, died, and then slowly settled to the bottom. Murray classified these biogenic sediments based on their composition. Foraminifera, single-celled organisms with calcium carbonate shells, were abundant in many areas. When they died, their shells accumulated on the seafloor, forming what Murray called foraminiferal ooze. In areas of high productivity, this ooze could accumulate at rates of inches per 1,000 years, slowly building up layers that recorded the history of ocean life. In some regions, particularly at great depths, the calcium carbonate shells dissolve before reaching the bottom. Seawater becomes more acidic with depth due to pressure and the accumulation of carbon dioxide from respiration. Below a certain depth, called the carbonate compensation depth, calcium carbonate dissolves completely. In these deep areas, only shells made of silica survived. Radiolaria, another type of microscopic organism, had silica skeletons, and their remains formed radiolarian ooze. Diatoms, microscopic algae with silica shells, were particularly abundant in cold productive waters, and diatom ooze was common in high-latitude regions. In the very deepest parts of the ocean, even the silica shells were dissolved or buried by other materials. Here, Murray found what he called red clay, an extremely fine sediment composed of clay minerals blown off continents as dust and settling slowly through the water, along with tiny particles of volcanic ash and even micrometeorites, extraterrestrial material that constantly rains down on Earth. This red clay accumulated so slowly that 1,000 years might produce only a fraction of an inch of deposit. Yet over millions of years, substantial thicknesses built up, recording the geological history of the deep ocean basins. Murray's understanding of ocean sediments would prove to be one of the expedition's lasting contributions. The patterns he discovered, the relationship between depth, productivity, and sediment type, remained valid and were refined but not fundamentally changed by later work. His classification system, modified and expanded, is still used by marine geologists today. When Challenger departed Japan in mid-June 1875, the route led east across the North Pacific. This would be one of the longest open ocean passages of the entire voyage, over 4,000 miles from Japan to Hawaii with no land in between. The vast emptiness of the Pacific was both monotonous and fascinating. Day after day, the the ship sailed across water that stretched to the horizon in every direction, unbroken by any sight of land, any sign of human presence beyond the ship itself. Daily life aboard Challenger during these long passages settled into routines that provided structure and purpose. Each day began at dawn, with the watch changing and the deck being swabbed. This ritual cleaning, performed every morning regardless of weather, served practical purposes in maintaining the wooden deck but also provided a sense of order and normalcy. The rhythmic scrubbing, the smell of salt water on wood, the gradual brightening of the sky, all marked the transition from night to day. Breakfast was served after the deck was cleaned, with the officers eating in the wardroom and the crew in the mess. The food, while adequate in quantity, was monotonous after months at sea. Salt pork and hardtack, dried peas and beans, rice and ship's biscuit formed the staples. Coffee or tea accompanied most meals, both for their stimulant effects and because the hot liquid made the meal more palatable. Fresh food was a distant memory between port stops, though occasionally fish could be caught, providing welcome variety. After breakfast, the scientific work would begin if a station was planned for that day. Not every day included a station. The ship needed to make progress across the vast Pacific, and stations were time-consuming. But every few days, sometimes daily in areas of particular interest, the order would be given to heave to. The ship would slow and stop, sails adjusted to balance each other and hold position against wind and current. The first task at each station was determining the ship's exact position. This required celestial navigation, measuring the angle of the sun above the horizon at noon using a sextant. The measurement, combined with the exact time determined by the ship's chronometers and mathematical tables compiled by astronomers, allowed calculation of latitude and longitude. This process, requiring skill and care, was the responsibility of the ship's navigator but was observed with interest by the scientists, who needed accurate positions to properly label their observations. Once the position was known, a sounding would be taken if depth measurement was among the station's objectives. This process, seemingly simple, was actually quite complex in deep water. A weighted line would be lowered over the side, marked at regular intervals to indicate depth. In shallow water, a few hundred fathoms or less, the process was relatively straightforward. But in the deep Pacific, soundings might reach 2,000 or 3,000 fathoms, requiring miles of rope to be paid out slowly and carefully. The challenge was determining when the weight actually touched bottom. The weight itself, typically 30 to 50 pounds of lead, fell through the water at a fairly constant rate. But as more rope paid out, its weight in the water increased. The rope itself, though relatively thin, weighed several pounds per 100 feet. With thousands of feet hanging in the water, the total weight became substantial. Distinguishing between the weight settling onto the bottom and the rope simply stretching under its own mass required experience and careful attention to subtle changes in how the line paid out. Current complicated the problem further. Even a slight current would cause the hanging rope to drift, angling away from vertical. This meant more rope was needed to reach a given depth, and the angle made it harder to detect when bottom was reached. In strong currents, accurate soundings became nearly impossible, and the operation might be abandoned until conditions improved. Once a sounding was successfully completed, the depth would be recorded in the station log along with the position, date, time, and other relevant information. The sounding weight, if it included a hollow core for capturing sediment, would be examined, and any sample would be carefully preserved for later analysis. Even a small amount of sediment could provide valuable information about seafloor composition and the organisms living there. Temperature measurements typically followed the sounding. Multiple millicursella thermometers would be attached to a line at different depths and lowered into the water. Each thermometer, in its brass protective case, recorded the maximum and minimum temperatures it experienced during its descent and ascent. After being brought back up, each thermometer would be read and its depth noted. The data would be recorded in the temperature log, building up a profile of how temperature varied from surface to depth. The process required patience and careful record keeping. It was easy to lose track of which thermometer had been at which depth, especially when multiple thermometers were deployed simultaneously. Labels and systematic procedures were essential. The data, once collected, would be compiled and analyzed after the expedition's return, revealing patterns of ocean temperature and circulation. Water sampling, when conducted, used specially designed bottles that could be closed at specific depths. These bottles, lowered open and then triggered to close by weight sent sliding down the line, captured samples that the chemist would later analyze. John Young Buchanan, the expedition's chemist, worked tirelessly during the voyage analyzing water samples for salinity, dissolved gases, and other chemical properties. His work, conducted in the cramped chemistry laboratory below decks, was meticulous and time-consuming but crucial for understanding ocean chemistry. Dredging or trawling, when included in a station, was the most time-consuming and labor-intensive operation. The appropriate equipment would be selected based on the depth, the type of bottom, and the target organisms. The dredge or trawl would be carefully attached to the dredging line, a heavy rope capable of supporting the weight of the equipment plus whatever it collected. Additional weights might be attached to help the dredge sink and stay on the bottom. The dredge would be swung out over the side using the dredging platform and winches, then lowered into the water. As it descended, the line would pay out steadily, coiled neatly to prevent tangles. In deep water, this descent could take hours. The sailors working the lines would rotate in shifts, as the work was physically demanding and monotonous. When the dredge reached bottom, the ship would move slowly forward under minimum sail, dragging the dredge across the seafloor. The distance dragged varied depending on conditions but was typically between half a mile and a mile. Too short a drag might not collect enough material, while too long a drag risked snagging on rocks or filling the dredge so full that it couldn't be raised. Hauling the dredge back up was even more laborious than lowering it. Now it was full of sediment and specimens, adding perhaps hundreds of pounds to the weight that had to be lifted. The line, stretched by the weight, had to be gathered in foot by foot. The winches, operated by teams of sailors, turned slowly and steadily. In the deepest water, raising a dredge could take 6 to 8 hours of continuous work. When the dredge finally broke the surface, there would be a moment of anticipation before it was swung aboard and its contents dumped onto the sorting tables. What would it contain? The scientists and crew gathered around as the mud and rocks and creatures spilled out. The first task was separating the obvious specimens, the larger organisms visible to the naked eye. These would be quickly sorted by type, with fish in one container, crustaceans in another, mollusks in a third, and so on. The mud itself, seemingly unpromising, would then be carefully washed through sieves of progressively finer mesh. Each sieving would reveal more organisms, smaller creatures that had been invisible in the mud. Tiny snails, minute worms, small brittle stars, all would be separated and preserved. Even after multiple washings, samples of the mud would be saved for later examination under microscopes, as experience had shown that countless microscopic organisms lived in the sediment. Processing a large dredge haul could take most of a day. Specimens had to be sorted, identified if possible, and placed in jars of preserving fluid. Each jar had to be labeled with details of where and when it was collected. The scientists made notes and sketches of particularly interesting specimens, trying to record color and form before preservation altered them. It was demanding work, requiring sustained attention and care, but it was also exciting, as nearly every haul contained species no one had seen before. The routine of scientific work provided structure to the long passages, but there were also times of rest and recreation. Sundays, weather permitting, were designated as rest days with no scientific work except essential weather observations. Religious services would be held on deck, led by the captain or by any qualified clergyman who might be aboard. The services, whether attended out of genuine religious conviction or simply as a break from routine, provided a communal activity that brought the ship's company together. In the evenings, after the day's work was complete, men would pursue various pastimes. Reading was popular among both officers and crew, and the ship carried a library of books that circulated among those who could read. Some men kept journals, recording their experiences and thoughts. Others wrote letters to family, knowing the letters couldn't be mailed until the next port but wanting to maintain the connection. Card games and other entertainments helped pass the time. Music, when someone had an instrument and the skill to play it, was especially valued. Songs, both traditional sea shanties and popular tunes from home, were sung. The singing served practical purposes too, coordinating work like raising anchor or setting sails, but also provided emotional expression and social bonding. The scientists formed a close-knit group, their shared interests and proximity creating bonds that went beyond professional collaboration. They discussed their observations and speculations, debated interpretations of data, and shared the excitement of new discoveries. Charles Wyville Thompson, as scientific director, worked to maintain good relations within the scientific team and between the scientists and naval officers. His diplomatic skills were as important as his scientific knowledge in ensuring the expedition's success. John Murray proved to be one of the most versatile members of the expedition. His practical experience at sea gave him credibility with the naval crew, while his scientific knowledge earned respect from the other scientists. He was willing to turn his hand to any task, from organizing specimens to conducting chemical analyses to helping with ship's work when needed. His good humor and energy helped maintain morale during difficult periods. The naval officers navigating the ship and managing the crew had their own challenges. Keeping a crew of over 200 men healthy, fed, and reasonably content during a voyage of years required constant attention. Discipline had to be maintained without being oppressive. Work had to be distributed fairly. Conflicts had to be resolved before they escalated. The petty officers and boatswains who directly supervised the sailors were crucial intermediaries between the officers and crew. The North Pacific crossing provided opportunities to study the open ocean far from any continental influence. The water was clear and deep blue, its color indicating low nutrient content and thus low biological productivity. Unlike coastal waters, which were often murky with suspended sediment and teeming with life, the open ocean at low latitudes was relatively barren. Nutrients, the minerals needed by microscopic algae to grow, were scarce in surface waters. Any nutrients released by decomposition sank and accumulated at depth, where there was no light for photosynthesis. Yet life was not absent. Careful sampling revealed communities of organisms adapted to the nutrient-poor environment. There were species of phytoplankton, microscopic algae, that could survive on the low nutrient levels. There were zooplankton, tiny animals that grazed on the phytoplankton or fed on each other. There were small fish that fed on the zooplankton, and larger fish that preyed on the smaller ones. There were squid, some of considerable size, that hunted in the darkness below the surface. And there were whales, following the concentrations of prey across vast distances of open ocean. The food web of the open ocean was different from coastal waters or from the rich polar seas. It was less productive overall, supporting smaller populations of organisms. But it covered such vast areas that the total amount of life was still substantial. Understanding how these open ocean ecosystems functioned, how energy and nutrients flowed through them, would be an ongoing challenge for oceanography. The Hawaiian Islands appeared as a welcome break in the vast monotony of the Pacific crossing. Challenger reached Honolulu on the island of Oahu in late July 1875, and the crew and scientists gratefully went ashore. Fresh food was abundant, particularly the tropical fruits that Hawaii produced in profusion. The volcanic landscape of the islands was dramatic and geologically fascinating. And the people, both native Hawaiians and the growing number of European and American settlers, were welcoming. Hawaii's isolation from other landmasses, over 2,000 miles from the nearest continent, had resulted in unique evolution. Many species found in Hawaii existed nowhere else on Earth. Birds had evolved into forms filling ecological niches occupied by different groups elsewhere. Plants showed distinctive adaptations to the volcanic soil and tropical climate. Even the marine life around the islands, while connected to the broader Pacific fauna, included endemic species found only in Hawaiian waters. The scientists explored the islands, collecting both terrestrial and marine specimens. They examined coral reefs, observing the rich diversity of life they supported. They collected shells along beaches, finding beautiful mollusks that would be prized by museums back in England. They ventured inland to see the tropical forests and the unique birds that inhabited them. From Honolulu, Challenger sailed south to Hilo Bay on the island of Hawaii, the largest in the chain and home to some of the world's most active volcanoes. Mauna Loa and Kilo were both active at the time, with Kilo in particular showing frequent eruptions. Some members of the expedition made excursions to observe the volcanoes, witnessing the dramatic spectacle of molten lava emerging from vents and flowing downslope toward the ocean. The volcanoes of Hawaii demonstrated the ongoing geological processes that shape the Earth. The Hawaiian Islands are the product of a hotspot, a plume of molten rock rising from deep in the Earth's mantle and melting through the overlying crust. As the Pacific tectonic plate moves slowly northwest over this hotspot, new volcanoes form, while older ones become dormant as they move away from the heat source. The Big Island of Hawaii is currently over the hotspot and thus has the active volcanoes. Older islands to the northwest are progressively more eroded and subsided, demonstrating the progression. This process of island formation had implications for understanding coral atolls, the ring-shaped islands that dotted the Pacific. Charles Darwin had proposed that atolls formed when volcanic islands slowly subsided, with coral reefs growing upward to keep pace, eventually forming a ring surrounding a lagoon after the original island had disappeared beneath the waves. The pattern of Hawaiian islands, with active volcanoes on the youngest island and progressively older and more eroded islands to the northwest, supported Darwin's theory of subsidence and reef growth. In mid-September 1875, Challenger departed Hawaii heading south toward Tahiti. This passage took the ship back across the equator into the South Pacific. The weather was generally favorable, with steady trade winds providing good sailing. The deep blue water, the flying fish skipping across the surface, the seabirds that occasionally appeared far from any land, all became familiar sights. But the passage to Tahiti was marked by tragedy. Rudolf von Willemoesum, one of the civilian scientists, had been unwell for some time. The exact nature of his illness is unclear from the expedition records, but it worsened during the crossing. Despite the care of his colleagues and the attention of the ship's surgeon, his condition deteriorated. He died during the passage and was buried at sea according to naval tradition, his body committed to the depths he had spent years studying. Willemoesum's death was a significant loss for the expedition. He had been a valued member of the scientific team, his expertise in microscopic organisms crucial for understanding plankton and other small creatures. He was also well-liked personally, and his death cast a somber mood over the ship. The scientists and crew were reminded that the voyage, for all its scientific excitement and adventure, was not without risk and hardship. Tahiti was reached in mid-September 1875, and the expedition spent time in the Society Islands. These islands, with their dramatic mountains and lush vegetation, their lagoons and coral reefs, embodied the romantic ideal of South Pacific paradise. The reality, while beautiful, was also complex. European contact had brought changes to traditional Polynesian culture, not all of them beneficial. Diseases introduced by Europeans had decimated island populations. Traditional ways were being displaced by Christianity and European economic systems. But the natural beauty remained, and the scientists took full advantage of the opportunity to study tropical marine and terrestrial ecosystems. The coral reefs surrounding the islands were particularly fascinating, demonstrating the incredible diversity of life that reefs support. Hundreds of species of fish, corals, mollusks, crustaceans, and other organisms could be found in even a small area of reef, all interacting in complex relationships of predation, competition, and symbiosis. From Tahiti, Challenger turned southeast, heading across the vast empty expanse of the southeastern Pacific toward South America. This portion of the Pacific is one of the most remote areas on Earth, far from any land, with few islands and little human activity. The ship sailed for weeks seeing nothing but ocean and sky, conducting stations at intervals but otherwise simply crossing the miles. The southeastern Pacific is notable for its low productivity despite being in tropical or subtropical latitudes. The cold Peru Current, flowing north along the coast of South America and then curving west into the open Pacific, brings cold water from the Southern Ocean. This cold water is rich in nutrients, and where it upwells along the coast of Peru and Chile, it supports enormous populations of fish and seabirds. But as it moves west into the open Pacific and warms, the nutrients are consumed by plankton, and productivity drops. The result is what oceanographers call an oceanic desert, water that is clear and blue but biologically impoverished. The Juan Fernandez Islands, off the coast of Chile, were reached in mid-November 1875. These isolated islands, about 400 miles west of the Chilean coast, are historically famous as the place where Alexander Selkirk was marooned in the early 1700s. Selkirk's experience as a castaway inspired Daniel Defoe's novel Robinson Crusoe, making the islands a subject of literary as well as geographical interest. The expedition surveyed the islands and collected specimens before continuing to Valparaiso, the major port on Chile's central coast. Valparaiso represented a significant milestone, the last major port stop before the final push to complete the circumnavigation and return to England. The ship had now been at sea for almost 3 years and had visited every major ocean basin. The route homeward would take Challenger around the southern tip of South America, north through the Atlantic, and finally back to England. Valparaiso provided a lengthy stop for rest, resupply, and ship maintenance. The vessel had been at sea almost constantly for 3 years, and both ship and crew showed the strain. Major repairs were carried out, supplies were loaded for the journey home, and everyone enjoyed the city and the chance to be on solid ground. 2 of the naval officers left the ship here to return to England by other means, having been promoted and needing to take up new assignments. From Valparaiso, the expedition made one more foray into the Pacific for additional scientific work before committing to the journey around South America. Stations were conducted west of Chile, adding to the comprehensive picture of Pacific oceanography that was being built. Then, as summer arrived in the southern hemisphere, Challenger turned toward the formidable waters around Cape Horn. The passage around the southern tip of South America was accomplished in January 1876, during the austral summer when conditions were most favorable. Even in summer, the waters around Cape Horn are notoriously difficult, with strong westerly winds, rough seas, and unpredictable weather. The meeting of the Atlantic and Pacific Oceans creates complex current patterns and often violent conditions. Many ships had been lost attempting to round the Horn, and caution was essential. Challenger spent most of January navigating the complex waterways of southern Chile and Tierra del Fuego. Rather than attempting the open ocean passage around Cape Horn, the ship threaded through the protected channels between islands, conducting surveys and scientific work in these relatively sheltered waters. The landscape was dramatic, with mountains rising directly from the sea, glacier carving into channels, and dense temperate rainforest covering lower slopes where it wasn't swept away by wind. The channels and straits of southern Chile provided unique environments for study. The water was cold, influenced by currents from the Southern Ocean. The high rainfall and glacial meltwater created brackish surface layers. The complex topography created varied habitats. Some channels had strong tidal currents, others were more placid. Some had rocky bottoms, others were floored with soft sediment. Each type of environment supported different communities of organisms. The expedition stopped at numerous locations with names that spoke of the region's history of exploration. The Gulf of Pinas, the Strait of Magellan named for Ferdinand Magellan who first navigated it, Port Famine where an early Spanish settlement had starved, channels and bays around Wellington Island and other remote islands. Each stop added to the scientific record and brought the expedition closer to emergence into the Atlantic. By late January 1876, Challenger had completed passage through the southern channels and emerged into the Atlantic Ocean. The ship was now on the final leg of the circumnavigation. Heading north along the coast of Argentina, the expedition called at the Falkland Islands in late January. These windswept islands, claimed by Britain but also desired by Argentina, were home to large colonies of seabirds and marine mammals. The scientists conducted surveys and collected specimens, adding South Atlantic materials to their vast collection. From the Falklands, Challenger continued north to Montevideo, Uruguay, reached in mid-February 1876. This was the last major port stop before the final Atlantic crossing to England. The ship was cleaned, painted, and prepared for the homecoming. Specimens were carefully packed and secured for the journey. Equipment was stored and laboratories were organized. Final reports were prepared to send ahead, informing the Royal Society and the Admiralty of the expedition's imminent return. The crew and scientists had mixed feelings as departure from Montevideo approached. There was eagerness to return home, to see families and friends after more than 3 years away, to sleep in beds that didn't move, to eat fresh food and have space and privacy. But there was also satisfaction in what had been accomplished, awareness that they had participated in something extraordinary. The expedition had succeeded beyond initial hopes, collecting vast quantities of specimens and data that would occupy scientists for decades. And there was perhaps some sadness that the adventure was ending, that the camaraderie and sense of shared purpose would disperse once they returned to normal life. From Montevideo, Challenger headed east across the South Atlantic. The route initially retraced paths followed earlier in the voyage, but additional stations were conducted to fill gaps in the data and to verify earlier measurements. Scientific work continued with the same diligence as at the start of the voyage, even though everyone was thinking about home. The commitment to thorough, systematic observation remained strong. Ascension Island was reached at the end of March 1876. This isolated volcanic island, rising steeply from deep ocean, served as a British outpost and refueling station. The expedition spent time conducting surveys around the island before continuing to the Cape Verde Islands, reached in early April. From Cape Verde, rather than heading directly to England, the route took the ship on one final loop out into the mid-Atlantic. This final loop was designed to complete the picture of Atlantic circulation and sediment distribution. Additional soundings and dredges added data points that would strengthen the conclusions about ocean processes. Water samples and temperature profiles verified the patterns that had been observed earlier. Even in these final weeks of the voyage, new specimens were collected, new observations were recorded, new data were added to the logbooks. In late April and early May 1876, the final stations of the expedition were completed. Each one was conducted with the same care and attention to detail that had characterized the entire voyage. The scientists knew that once they reached England, their at-sea work would be finished. Any gaps in the data, any missing observations, could not be filled later. So they ensured that everything was complete, that all measurements were taken, that all specimens were properly preserved and labeled. The final approach to Europe took Challenger first to Vigo, Spain, in late May. This was the first European port since departing England over 3 years earlier. The sight of familiar coastlines, The sounds of European languages, the proximity to home after so long away stirred deep emotions. From Vigo, it was just a short sail along the coast and across the English Channel to England. On May 24, 1876, HMS Challenger arrived at Spithead near Portsmouth, completing one of the greatest scientific voyages in history. The ship had been at sea for 713 days out of the intervening 1,250 days since departure. It had covered 68,890 nautical miles, equivalent to sailing around the world nearly 3 times. The expedition had stopped at 362 stations to conduct comprehensive observations. 492 deep-sea soundings had been taken. 133 bottom dredges had been deployed. 151 open water trawls had been conducted. 263 serial water temperature observations had been completed. Approximately 4,700 new species of marine life had been discovered. Of the original crew and scientific staff of 237, only 144 returned. The others had died, deserted, been discharged due to illness, or left for other assignments. The 3.5 years at sea had taken a toll in lives and health. But those who returned had accomplished something that would echo through the history of science. The return of Challenger was celebrated but also marked the beginning of a new phase of work. The specimens and data collected during the voyage needed to be analyzed and published. This would prove to be an even more daunting task than the voyage itself. The sheer volume of material was overwhelming. Thousands of preserved specimens needed to be identified, described, and illustrated. Temperature and depth measurements needed to be compiled and analyzed. Water chemistry data needed to be interpreted. Sediment samples needed to be examined in detail. The geographical and navigational information needed to be turned into maps and charts. Charles Wyville Thompson took on responsibility for overseeing this work. The Challenger office was established in Edinburgh with government funding to support the publication effort. Thompson began assembling a team of specialists from around the world, sending specimens to experts in different groups of organisms. Each specialist would study their assigned group, describe new species, and write a report on their findings. The process was much slower and more expensive than anyone had anticipated. Some specialists worked quickly, producing reports within a few years. Others were slower, taking a decade or more. Some groups of organisms were relatively straightforward to study, while others required extensive anatomical work. Funding was sometimes inadequate, causing delays. Thompson himself fell ill from the strain of managing the project, dying in 1882 having seen only a small portion of the results published. John Murray took over direction of the Challenger office after Thompson's death. Murray, who had been Thompson's closest collaborator during the voyage, proved to be an effective manager. He kept the project moving forward, securing additional funding when needed, pushing specialists to complete their work, and maintaining quality standards. Murray also made major scientific contributions himself, particularly in the area of marine sediments where his expertise was unmatched. The publication of the Challenger reports became a multi-decade effort. The first volumes appeared in the early 1880s. The final volume was published in 1895, 19 years after the expedition's return. The complete report of the scientific results of the exploring voyage of HMS Challenger during the years 1873 to 76 comprised 50 volumes totaling over 29,500 pages. The reports contain thousands of illustrations, including detailed scientific drawings of specimens, maps and charts showing the ship's route and oceanographic features, and photographs of equipment and operations. The Challenger reports became standard references in marine science. They were found in scientific libraries around the world and were cited in research papers for generations. The descriptions of new species established the baseline for understanding marine biodiversity. The oceanographic data provided the foundation for physical and chemical oceanography. The sediment studies informed marine geology. The comprehensive nature of the work, covering every aspect of ocean science from biology to geology to chemistry to physics, made the reports uniquely valuable. Many of the scientists who contributed to the Challenger reports went on to distinguished careers. The experience of working with Challenger specimens and data shaped their thinking and research programs. Graduate students learned by studying Challenger materials. Museum collections built around Challenger specimens became research centers. The expedition's influence rippled outward through the scientific community for decades. The specimens themselves have proved to be lasting resources for science. Many Challenger specimens are still preserved in museums, particularly the Natural History Museum in London, where the majority of the collection resides. These specimens, collected over a century and 40 years ago, are still studied by scientists today. Modern techniques, including DNA analysis, allow researchers to extract information from the specimens that the original collectors could not have imagined. Specimens that were identified as one species are sometimes found to actually be several cryptic species when examined with molecular methods. The preserved tissues contain valuable genetic information about historical populations, allowing comparisons with modern populations to detect changes over time. The impact of the Challenger expedition on oceanography as a discipline cannot be overstated. Before Challenger, oceanography barely existed as a coherent field. There were individuals working on various aspects of marine science, but they were scattered across different disciplines and institutions. After Challenger, oceanography emerged as a distinct field with shared methods, questions, and frameworks for understanding the ocean. The systematic approach pioneered by Challenger, conducting standardized observations at regular stations, became the model for subsequent oceanographic expeditions. The equipment designed or refined during the expedition, from dredges to thermometers to water samplers, continued to be used for decades with only incremental improvements. The focus on comprehensive observation, measuring multiple parameters at each station rather than targeting just one question, established a tradition of broad-based ocean surveys. Educational programs in oceanography began to appear at universities following the Challenger expedition. The University of Edinburgh, Thompson's institution, became an early centre for oceanographic education. Other universities in Britain, Europe, and North America followed. Students could now pursue formal training in oceanography rather than coming to the field from other disciplines. This professionalization of the field accelerated the growth of oceanographic knowledge. Government support for oceanographic research increased dramatically after Challenger demonstrated its value. Britain, Germany, the United States, Russia, and other nations established oceanographic institutes and funded research vessels. The practical applications of ocean knowledge, from fisheries management to naval operations to climate prediction, justified continued investment. But there was also recognition that basic research, exploration for the sake of knowledge, had value beyond immediate practical returns. The Challenger expedition inspired subsequent expeditions that built on its work. The German Valdivia expedition of 1898–99 explored the deep-sea fauna of the Atlantic and Indian Oceans. The Danish Dana expeditions in the early 20th century focused on plankton and deep-sea fish. The Discovery investigations of the 1920s and 30s studied the Southern Ocean in detail, building on Challenger's pioneering work in Antarctic waters. Each of these expeditions acknowledged Challenger as their inspiration and model. The name Challenger itself became synonymous with ocean exploration. When Britain built a new oceanographic research vessel in the 1930s, it was christened HMS Challenger II, explicitly connecting it to the original vessel. In 1951, Challenger II measured the depth of the Mariana Trench near the site of the original Challenger's deepest sounding, finding it even deeper than the 19th century expedition had measured. The deep-sea submersible trees descended to the bottom of the Challenger Deep in 1960, the deepest dive ever made. More recently, filmmaker James Cameron piloted a submersible to the Challenger Deep in 2012, capturing the first video footage of the deepest place on Earth. Even NASA's Space Shuttle Challenger, tragically lost in 1986, was named in honor of the oceanographic vessel, recognizing the parallel between ocean exploration and space exploration. Both involve journeys into hostile environments where humans cannot survive without technology. Both expand the boundaries of human knowledge and experience. Both inspire and demonstrate what can be accomplished through dedication, skill, and courage. The scientific legacy of the Challenger expedition remains relevant today. The basic questions that drove the expedition, questions about ocean circulation, the distribution of life in the ocean, the chemistry of seawater, the geology of the seafloor, remain central to modern oceanography. The answers have been refined and expanded with better technology and deeper understanding, but the fundamental framework established by Challenger endures. Modern oceanography benefits from capabilities the Challenger scientists could barely imagine. Satellites orbit overhead, measuring ocean surface temperature, color, and height with extraordinary precision. Autonomous vehicles patrol the ocean depths, collecting data without human intervention. Ships carry multi-beam sonar that can map the seafloor in high resolution. Sensors measure dozens of parameters simultaneously and transmit data in real time. Computer models simulate ocean processes and predict future changes. Yet despite all these advances, the ocean remains incompletely known. Vast areas of the seafloor have never been mapped at high resolution. Most of the ocean's volume has never been directly sampled. Many species remain undiscovered, particularly in the deep sea. The full complexity of ocean processes, from turbulent mixing to biological communities to chemical cycles, is still being unraveled. The work that Challenger began continues, carried forward by new generations of oceanographers. Climate change has given particular urgency to understanding the ocean. The ocean absorbs over 90% of the excess heat trapped by greenhouse gases, moderating atmospheric warming but storing up future consequences. The ocean absorbs about a quarter of the carbon dioxide emitted by human activities, slowing the build-up in the atmosphere but causing ocean acidification that affects marine life. Changes in ocean circulation could alter climate patterns worldwide. Understanding these processes requires the kind of systematic global observations that Challenger pioneered, though now on a much larger scale and with much greater continuity. The deep-sea ecosystems that Challenger discovered are now known to be more diverse and complex than even the expedition scientists imagined. Hydrothermal vents, discovered in the 1970s, support communities based on chemical energy rather than sunlight, a form of ecosystem that was completely unexpected. Cold seeps, where methane and hydrogen sulfide leak from the seafloor, host similar chemosynthetic communities. The diversity of deep-sea life is extraordinary, with new species still being described at a rapid rate. These deep-sea ecosystems are also now recognized as vulnerable. Deep-sea trawling for fish destroys slow-growing coral communities. Mining for minerals, particularly the manganese nodules that Challenger first documented, threatens to disturb vast areas of seafloor. Climate change may affect deep-sea environments through warming, acidification, and changes in oxygen levels. Protecting these ecosystems requires understanding them, the same goal that motivated the Challenger expedition. As modern oceanographers continue their work, they often reflect on the achievements of their predecessors aboard Challenger. The dedication to thorough observation, the systematic approach to data collection, the commitment to comprehensive study rather than narrow specialization, these remain ideals worth emulating. The willingness to endure hardship and discomfort in pursuit of knowledge, the sense of wonder at what the ocean contains, the recognition that exploration has value beyond immediate practical applications, these too are part of Challenger's legacy. The story of the Challenger expedition is ultimately a human story. It's the story of scientists driven by curiosity to explore the unknown. It's the story of sailors doing difficult, dangerous work far from home. It's the story of institutional support, with the Royal Society and Royal Navy collaborating to make the expedition possible. It's the story of international cooperation, with scientists from many nations contributing to analyzing the results. It's the story of persistence, with the publication of results taking 19 years after the voyage ended. It's the story of how individual effort and institutional commitment can together accomplish things that neither could achieve alone. The men who sailed aboard Challenger, both the scientists and the crew, were ordinary people who participated in something extraordinary. They were not superhuman. They got tired, they got bored, they quarreled occasionally, they made mistakes. But they also showed dedication, skill, and courage. They did work that was often tedious but always careful. They persevered through hardships. And they returned with knowledge that changed human understanding of our planet. As you drift toward sleep, perhaps you can imagine yourself aboard HMS Challenger, feeling the gentle roll of the ship at anchor while a dredge is lowered into the depths. You might imagine the excitement when the dredge comes up, filled with mud and rocks and strange creatures that no one has ever seen before. You might imagine the satisfaction of completing another station, another set of observations, another small piece added to the growing picture of the ocean. You might imagine the long passages between stations, the ship sailing across empty ocean under a sky full of stars, moving steadily toward the next destination and the next discovery. The ocean that the Challenger expedition explored is still there, still vast, still full of mysteries. Though much has been learned in the century and a half since Challenger sailed, the ocean retains its capacity to surprise and fascinate. New expeditions continue the work, using modern tools to probe deeper and understand more completely. But they build on the foundation that Challenger laid, the recognition that systematic observation and careful study can reveal the ocean's secrets. The 50 volumes of the Challenger reports, those thousands of pages of detailed observations and descriptions, represent something profound about the scientific enterprise. They show that knowledge is built slowly, through patient accumulation of observations, through careful comparison and analysis, through the combined efforts of many people over many years. There are no shortcuts to understanding. The Challenger scientists understood this, and they committed themselves to doing the work thoroughly, knowing that others would build on their efforts. The specimens they collected, the measurements they took, the maps they made, all contributed to a comprehensive picture of the ocean. No single observation was revolutionary by itself. But together, they transformed understanding. This is how science works, not through sudden dramatic breakthroughs but through steady accumulation of evidence, gradual emergence of patterns, slow construction of coherent explanations. The biological discoveries alone would have justified the expedition. The approximately 4,700 new species described from Challenger collections represented an enormous expansion of known marine biodiversity. Many of these species were not just new but represented entirely new groups, new families, or even new orders of organisms. The glass sponges brought up from deep water, with their delicate silica skeletons, were unlike anything previously known. The sea spiders with impossibly thin legs spanning inches, the sea cucumbers in bizarre shapes and sizes, the worms adapted to every conceivable niche, all demonstrated the incredible diversity of ocean life. The distribution patterns revealed by the specimens were equally fascinating. Some species were found only in specific regions, adapted to local conditions. Others were widespread, found in multiple ocean basins at similar depths. Some species varied predictably with depth, occurring in distinct zones. Others varied with latitude, tracking temperature zones. Still others varied with substrate, occurring on rocky bottoms but not on mud, or vice versa. These patterns of distribution reflected the ecology and evolution of marine organisms. Understanding why particular species occurred where they did required understanding their environmental requirements, their reproductive strategies, their dispersal mechanisms, their interactions with other species. The Challenger collections provided the raw data that would fuel decades of research in marine ecology and biogeography. The adaptations of deep-sea organisms to their extreme environment were particularly remarkable. Bioluminescence, the ability to produce light through chemical reactions, was common among deep-sea creatures. Fish, squid, shrimp, and other organisms possessed light organs that glowed in various colors and patterns. Some used their lights to attract prey, dangling a luminous lure to draw victims close. Others used lights to communicate, signaling potential mates or warning rivals. Still others used lights as camouflage, counter-illuminating their bellies to match the dim light from above and avoid casting a silhouette that predators below could detect. The body forms of deep-sea fish showed remarkable specializations. Many had large mouths armed with long teeth, allowing them to capture and swallow prey larger than themselves. In an environment where food was scarce and encounters with prey were infrequent, the ability to consume whatever came along, regardless of size, was valuable. Some fish had distensible stomachs that could expand to accommodate large meals. Others had hinged jaws that could open extraordinarily wide. Many deep-sea organisms had reduced or absent eyes, since sight was useless in total darkness. But they had enhanced other senses to compensate. Lateral lines, sensory organs that detect water movement, were often enlarged, allowing detection of prey or predators from a distance. Chemical senses were acute, with some organisms able to detect tiny concentrations of scents or tastes. Some fish had elongated fin rays or barbels that trailed through the water like fishing lines, sensing any disturbance. The colors of deep-sea organisms were often striking, though this wouldn't be apparent in the darkness of their natural environment. Many were brilliant red, a color that appears black at depth where no red light penetrates. This provided effective camouflage while also potentially serving functions during rare encounters with other individuals. Others were silver or translucent, making them nearly invisible. Some were black, absorbing any stray light. The color patterns revealed by Challenger specimens, carefully recorded by the expedition's artist before preservation, provided clues to the ecology of deep-sea life. The physiological adaptations were equally remarkable though less visible. Deep-sea organisms had to withstand pressures that would collapse normal cellular structures. They achieved this through various means, including trimethylamine oxide and other organic compounds that counteract pressure effects, flexible body structures that compressed uniformly rather than being crushed, and absence of gas-filled spaces that would collapse. Understanding these adaptations would eventually contribute to medical research on hyperbaric conditions and would inform the design of deep-sea exploration vehicles. The geological findings of the Challenger expedition had implications that wouldn't be fully appreciated until decades later. The discovery of the Mid-Atlantic Ridge, the mapping of oceanic trenches, the documentation of volcanic island chains, all provided data that would eventually contribute to the theory of plate tectonics. In the 1870s, geologists had no framework for understanding these features. Continental drift had been proposed but was not widely accepted. The mechanism driving geological processes was unknown. It would take until the 1960s for plate tectonic theory to be developed, explaining the ocean ridges as spreading centers where new crust is created, the trenches as subduction zones where old crust is consumed, and the island chains as traces of hotspots in the mantle. When this synthesis finally occurred, Challenger data played a crucial role. The systematic mapping of ocean floor topography provided evidence that demanded explanation. The patterns of sediment thickness and composition fit perfectly with spreading seafloor models. The chemical oceanographic findings established foundational understanding of seawater composition. John Young Buchanan's meticulous analyses showed that while total salinity varied from place to place, the ratios of major dissolved elements remained remarkably constant. This principle of constant proportions, sometimes called the Marsit principle after an earlier researcher who first proposed it, became fundamental to chemical oceanography. It meant that measuring a single property like chloride concentration could determine total salinity with good accuracy. Buchanan also documented variations in dissolved oxygen with depth. High near the surface where it was absorbed from the atmosphere and produced by photosynthesis, oxygen decreased at mid-depths where organisms consumed it through respiration, then often increased again near the bottom where deep currents carried oxygen-rich water from polar regions. This oxygen profile was another key to understanding ocean circulation and would have important implications for the distribution of marine life, as organisms need oxygen to survive. The physical oceanographic measurements established temperature and salinity structures that revealed ocean circulation patterns. The cold bottom water found at all latitudes clearly originated in polar regions and flowed along the bottom toward the equator. The warm surface currents like the Gulf Stream and Kuroshio carried heat from tropics to higher latitudes. The intermediate depths showed complex patterns of water masses with distinct characteristics, each telling a story of where that water had been and what processes had affected it. These circulation patterns have profound effects on climate. The ocean is Earth's primary heat transport mechanism, moving more heat from equator to poles than the atmosphere does. Changes in ocean circulation can trigger climate shifts. The deep overturning circulation, sometimes called the thermohaline circulation because it's driven by temperature and salinity differences, operates on timescales of centuries to millennia, slowly turning over the entire ocean. Understanding this circulation is crucial for predicting climate change, as alterations to the system could have dramatic and long-lasting effects. The expedition also made important contributions to understanding coral reefs and their formation. Charles Darwin's theory, proposing that fringing reefs could become barrier reefs and then atolls as islands slowly subsided, was generally supported by Challenger observations. The expedition documented reefs at various stages of this progression, from actively growing fringing reefs around volcanic islands to barrier reefs separated from islands by lagoons to atolls where the original island had completely subsided below sea level, leaving only a ring of coral. This understanding of reef formation had implications for geology, demonstrating that oceanic islands slowly sank over geological time, and for biology, showing how coral growth could keep pace with subsidence over millions of years. The diversity of life supported by coral reefs, documented in detail by Challenger scientists, revealed reefs as among Earth's most productive ecosystems, rivaling tropical rainforests in species diversity despite covering much smaller areas. The ethnographic observations made during port stops, while not the expedition's primary focus, added to anthropological knowledge of Pacific peoples. The scientists and ship's artists documented traditional lifestyles, material culture, and social structures of islanders encountered from Fiji to Hawaii. While these observations reflected the Victorian British perspective and assumptions of their time, they nevertheless preserved information about cultures that were rapidly changing due to European contact. The expedition's legacy extended beyond the scientific results to influence how future ocean research would be conducted. The model of having civilian scientists aboard a naval vessel, with scientific direction of the research program but naval control of the ship's operation, proved effective and was adopted by later expeditions. The systematic approach of stopping at regular stations to take multiple types of measurements became standard practice. The emphasis on preserving specimens for later expert examination, rather than trying to identify everything immediately, allowed for thorough study by specialists. The international collaboration in analyzing Challenger results established a pattern that would become characteristic of oceanography. The ocean doesn't respect political boundaries, and understanding it requires observations from all regions. Sharing data and specimens across national borders, having scientists from different countries contribute to analyzing results, benefits everyone by expanding knowledge. This tradition of international cooperation, begun by the Challenger expedition, continues in modern oceanography through programs like the International Ocean Discovery Program and the Global Ocean Observing System. The public engagement generated by the Challenger expedition helped build support for ocean science. Newspaper accounts of the discoveries reached wide audiences. Specimens displayed in museums attracted visitors who marveled at bizarre creatures from the deep. Popular books written by expedition members introduced oceanography to readers who had never before considered what lay beneath the ocean's surface. This public interest translated into political support for funding future ocean research and for establishing oceanographic institutions. Universities and research institutes founded in the decades after Challenger's return explicitly cited the expedition as inspiration. The Marine Biological Laboratory at Plymouth, the Station Zoologica in Naples, the Scripps Institution of Oceanography, and many other centers of ocean research trace their origins to the enthusiasm generated by Challenger. These institutions trained successive generations of oceanographers, ensuring that the momentum begun by Challenger would continue. The technological development spurred by Challenger's needs also had lasting impact. Better thermometers, improved dredges, more reliable water samplers, all were designed or refined for the expedition and then adopted by others. The shipboard laboratories and the procedures for preserving specimens influenced how later expeditions equipped their vessels. Even seemingly mundane innovations like better ways to coil and manage miles of rope contributed to making deep ocean work more feasible. The cartographic legacy included detailed charts showing ocean depths, currents, and sediment distributions. These charts were used by navies for planning submarine operations and mining companies for locating resources. They were incorporated into atlases and textbooks, educating generations about ocean geography. Modern bathymetric maps, created with sophisticated sonar and satellite data, show much greater detail but still acknowledge the Challenger expedition as establishing the basic framework. As you rest, let the story of the Challenger expedition remind you that patient effort yields lasting results. The scientists and sailors who spent 3.5 years at sea, collecting specimens and taking measurements, could not have known how influential their work would prove to be. But they did it carefully and thoroughly, and that care has given their work enduring value. This is a lesson that extends beyond science. Any work done carefully, with attention to detail and commitment to excellence, has the potential to matter far into the future. The ocean continues its eternal rhythms, indifferent to human observation but knowable through patient study. Currents flow, carrying water and heat and nutrients around the globe. Organisms live and die at every depth from surface to seafloor. Sediments slowly accumulate, recording the history of the ocean and its life. All of these processes, documented by Challenger and studied by subsequent expeditions, continue without pause. Tonight, as you sleep, research vessels continue the work that Challenger began. Somewhere in the world ocean, scientists are conducting observations, collecting specimens, measuring properties of seawater, mapping the seafloor. They use technology that would seem like magic to the Challenger scientists, but they pursue the same fundamental goal: understanding the ocean. They are part of a tradition that stretches back to 1872, when HMS Challenger first sailed from Portsmouth on a voyage into the unknown. The legacy of the Challenger expedition is not just the specimens in museums or the data in reports. It's the recognition that exploration has value, that seeking knowledge is a worthwhile endeavor, that understanding our world makes us more fully human. This legacy continues to inspire not only scientists but anyone who looks at the ocean and wonders what lies beneath, anyone who values knowledge for its own sake, anyone who believes that the effort to understand is worthwhile even when the path is long and difficult. So rest now, knowing that the spirit of exploration endures. The mysteries of the ocean still call to those brave enough to pursue them. The work begun by HMS Challenger in 1872 continues in research vessels and laboratories and universities around the world. Each generation adds to the knowledge, building on the foundation laid by those pioneering scientists and sailors who first systematically explored the ocean depths. Sleep well and dream of discovery. Dream of distant seas and deep trenches, of creatures adapted to darkness and pressure, of currents carrying water across thousands of miles, of sediments recording millions of years of history. Dream of the Challenger sailing across empty ocean, of scientists sorting through mud to find treasures, of sailors working winches to bring up dredges from miles below. Dream of the satisfaction of completing work that matters, of contributing to knowledge that will endure. The Challenger expedition showed what could be accomplished when curiosity, resources, and commitment came together. It showed that systematic observation could reveal patterns and principles. It showed that international cooperation could advance knowledge. It showed that both the journey and the destination have value, that the process of exploration is as important as the discoveries made. These lessons remain relevant today, reminding us that great things are possible when we dedicate ourselves to understanding our world. And if you enjoyed this journey into the history of oceanographic exploration, if this story helped you relax and drift towards sleep, perhaps you'll like and subscribe to join us for future voyages into science and history. There are countless stories of exploration and discovery, of people who ventured into the unknown and returned with knowledge. Each story reveals something about human nature, about our curiosity and courage, about our determination to understand. Until next time, sleep well and let your dreams carry you to distant oceans and deep mysteries. The ocean waits, patient and eternal, as it has waited for billions of years. The Challenger expedition touched only a tiny fraction of its vastness, collected only a minute sample of its diversity, measured only scattered points in its immense volume. Yet even that small beginning was enough to transform understanding, to reveal the ocean as a dynamic, complex, life-filled system rather than a static void. If so much could be learned from one voyage, imagine what remains to be discovered. The ocean holds secrets still, waiting for future challenges to reveal them.